All right, hello everyone, and welcome to our Chapter 10 review. If you have any questions on this worksheet after this video, please do not hesitate to reach out and I am happy to help you. So first we are starting with number 1, and we have an equation here. Fe2O3 plus C reacts to form Fe plus CO2. So this is an unbalanced equation, and we know in stoichiometry, in order to convert between one substance and another, we do have to have a balanced chemical equation. So first let's start off number 1 by balancing this equation. So starting off with iron, on the left side, I have 2 irons. On the right side, I only have 1, so I'm going to multiply this by 2. Then I go to my oxygens. I have 3 and 2, so since I can't just manipulate one number, I need to find the common multiple. So the common multiple of 3 and 2 is going to be 6, which means I need to multiply Fe2O3 by 2 and then CO2 by 3. And that is going to change our number of irons. So now on the left side, I have a total of 4 irons, so I need to make this coefficient a 4. And now I can balance my carbons. I have 3 carbons on the right, so I need to put a 3 here, and now it is balanced. Part A says how many moles of carbon are required to completely react with 14.251 moles of Fe2O3. So with any type of stoichiometry problem, you're always going to start with what number you're given. I always find that easiest to make sure I'm canceling out the correct units and getting to what I want. So I'm starting out with 14.251 moles of Fe2O3. And in this question, I am looking for moles of carbon. So with stoichiometry, remember, we are using the mole ratio to go from one substance to the other. So if I'm already in moles, I can go right to our mole ratio. So whatever I'm trying to get rid of is going to go on the bottom. So I'm trying to get rid of moles of Fe2O3. And I want to get to moles of carbon, so that's going to go on the top. And since I'm solving for moles of carbon, I'll be done after that. Now this fraction here is what's called our mole ratio. So we want to get those numbers from our balanced chemical equation. So we have 2 moles of Fe2O3, and then we have 3 moles of carbon. And again, that's from our balanced chemical equation up here. So now that my units cancel out and I'm left with moles of carbon, my last thing to do is to solve with my math. So I have 14.251 times 3 divided by 2, and that's going to give us 21.377 moles of carbon. So that's our answer for part A. And the reason I answered part A in 5 sig figs is because the number I was given was also 5 sig figs. So now moving on to part B, it says how many moles of Fe2O3 must react to generate 0.986 moles of pure iron. So again, we're going to start with the number that we are given. So we have 0.986 moles of iron, which is Fe. And it's asking for moles of Fe2O3. So these problems are pretty much as basic as they get because you are given moles and you want to end up with moles. So it's just the mole to mole ratio. So if we want to get rid of moles of iron, that's going to go on the bottom. If we want to get to moles of Fe2O3, that's going to go on the top. Remember, this is called your mole ratio, and you get the numbers for your mole ratio from the balanced chemical equation. So moles of iron is 4, and moles of Fe2O3 is 2. So we're going to take 0.986 and multiply that by 0.5. And that gives us 0.493 moles of Fe2O3. All right, and then part C of number 1 says how many moles of carbon dioxide will be generated if 2.774 moles of carbon completely reacts. So again, we're starting with the number that we are given. We have 2.774 moles of carbon, and we are looking for moles of CO2. So again, just a mole to mole ratio. So we want to get rid of moles of carbon, and we want to end up with moles of carbon dioxide. So now this is the mole ratio, so the numbers come from the balanced chemical equation. We have 3 moles of carbon dioxide and we have 3 moles of carbon. So the number is going to be the same. Since we are given 4 sig figs, we just need to answer in the same number of sig figs. So it's 2.774 moles of carbon dioxide. And remember, that's because our moles of carbon have now been canceled out. So those units are gone. So that is how you do number 1. Again, this is one of the more basic problems because you're given moles and you're asked for moles. So all you have to do is the mole ratio. As we move along in this worksheet, it's going to get a little more complicated with some more steps. So number 2 says when nitroglycerin explodes, the following reaction occurs. It is already balanced. If 0.398 moles of nitroglycerin explodes, how many moles of each product would be formed? So again, we are given moles, and it wants moles of all 4 of the products. So all we're going to do is take our original amount and use the mole ratio to get to each of our products. So let's start out with our first product, which is CO2. So I have 0.398 moles of C3H5ONO2 3. And I want to get rid of those. So it's going to go on the bottom. Moles of C3H5ONO2 3. And I want to get to moles of carbon dioxide. So that's going to be on the top. And remember, this is called our mole ratio. So those numbers come from the balanced chemical equation. So I have 4 moles of my nitroglycerin. And I have 12 moles of carbon dioxide. So I'm going to go ahead and do in my calculator 0.398 times 12, press equals, and divide by 4, or 0.398 times 3. And that gives us 1.19 moles of carbon dioxide. And I put that into 3 sig figs because our number given to us, 0.398, was 3 sig figs. So now moving on to water, I'm going to start with the same amount of nitroglycerin. And because I'm already in moles, I'm just going to use my mole ratio to get to moles of water. And I want to cancel out my moles of nitroglycerin. So C3H5ONO2 3. And this is again the mole ratio, so we want to get those from our balanced chemical equation. We have 10 moles of water and we have 4 moles of nitroglycerin. So in our calculator, we'll do 0.398 times 10 divided by 4. And that gives us 0.995 moles of water. Now moving on to N2, our next product. Again, we're starting with our same amount of nitroglycerin and then using the mole ratio to go from nitroglycerin into N2. And I get those numbers from my balanced chemical equation. So 6 moles of N2 and 4 moles of nitroglycerin. Then in my calculator, I will do 0.398 times 6 divided by 4, which gets me 0.597 moles of N2. And for my last product, oxygen gas, again, I'm starting with my 0.398 moles of nitroglycerin and multiplying that by my mole ratio. Again, I want to get rid of moles of nitroglycerin, so those are going to be in my denominator. And I'm going to get to moles of O2, that's going to be my numerator. So in my calculator, I will just do 0.398 divided by 4. And that gives me 0.0995 moles of oxygen gas. And those are my 4 answers for number 2. Number 3 says the element phosphorus naturally occurs as P4. It reacts readily with magnesium according to the following equation. This is unbalanced. So remember, the first step in stoichiometry is you need to balance your chemical equation. So looking at magnesium, I have 3 moles of magnesium on the right and 2 phosphorus. So because I have to multiply that by 2 for my P4, I'm going to start with that. And then you can see I now have 6 magnesiums on the right. So I need to make this 6 on the left. And now I am balanced. Number 3 says, what mass in grams of P4 is required to completely react with 73.4 grams of magnesium? So like I said, it's always easiest for me to start with what I'm given and figure out how I get to what they want. So I'm starting with 73.4 grams of magnesium, and I'm solving for mass of P4. So I have to go from magnesium to P4, and I have to do a mass-to-mass problem. So remember, when we're doing stoichiometry, you have to be in moles to actually do the mole ratio to convert between your two substances. So because I'm starting with grams of magnesium, my first step is to get into moles of magnesium. And whenever we need to go from grams to moles or moles to grams, we're using the periodic table because that gives us a molar mass, which is grams per 1 mole. So if I just want magnesium, I know 1 mole of magnesium is equal to the molar mass on the periodic table. And on the periodic table, magnesium is 24.305 grams. Now that I'm in moles of magnesium, I can do the mole ratio to go from magnesium to P4. So whatever numerator unit you have here is going to go on the denominator of the next. So I'm trying to get rid of moles of magnesium, and I want to end up with moles of P4. Remember, this mole ratio here is the only time in stoichiometry where you get the numbers from the balanced chemical equation. So we have a coefficient of 1 for P4 and a coefficient of 6 for magnesium. Now, if the question was asking for moles of P4, I would be done, but it did not. It's asking for grams. So I have one more step, and I know if I'm trying to get to grams, I'm going to be using the periodic table. So I know in 1 mole of P4, that's going to be equal to the molar mass of P4. Now here, it's not just 1 phosphorus, it's 4 of them. So I need to take my 30.974 and I need to multiply that by 4. And that gives me a molar mass for P4 of 123.896 grams. So now, if you want to check your units, we can see our grams of magnesium is gone, our moles of magnesium is gone, and our moles of P4 is gone, and all we're left with is grams of P4, which is exactly what it's asking for. So let's go ahead and do the math. So in our calculator, we will do 73.4 divided by 24.305, press equals, divide that number by 6, press equals, and then multiply that number by 123.896. We are given our original number as 73.4, which is 3 significant figures. So in our calculator, we end up getting 62.36005. So 3 significant figures would be here. 6 does in fact round up. So our final answer would be 62.4 grams of P4. Number 4 says ammonia reacts with oxygen according to the following equation. So I can see I have an unbalanced equation. I need to balance it. The first thing I notice is always this O2 molecule. If I have an O2 molecule on one side, that means I have to have even numbers of oxygens on the right. And my eye is immediately drawn to this oxygen here, which is odd. So I'm going to start with water and what I have to do to make sure it is even. So looking at hydrogens on the left side, I have 3 hydrogens. So if I wanted to balance my hydrogens, I'd have to have our multiple of 6 because I have 3 on the left and 2 on the right. But if I did multiples of 6, I would have to put a 3 here, which would make that oxygen odd. So instead of multiplying by 3, I'm going to double that and multiply by 6. So I have 12 hydrogens on each side. And now that I have 12 hydrogens on the right, I need to make 12 hydrogens on the left. And now I can go ahead and balance everything else. So I have 4 nitrogens and 1 nitrogen, so I'm going to put a 4 here. My hydrogens are already balanced, so let's go ahead and address our oxygens. So on the right, we have 4 times 2, which is 8, and 6 times 1, which is 6. So 8 plus 6 is 14. 14 divided by 2 is going to be 7. So this is our balanced chemical equation. So this question says how many molecules of water. Whenever you see the word molecules or atoms or formula units, you need to immediately think of Avogadro's number. So it's wanting for molecules of water, and we are given grams of ammonia, which is NH3. So again, we're always starting with what we're given, which is 191.4 grams of ammonia. And we need to go all the way to molecules of water. So I know my stoichiometry or my mole ratio is going to be going from NH3 to H2O, but first I have to be in moles to even use that. So first step is to use our periodic table to get rid of grams and to get into moles of NH3. So I know from my periodic table, 1 mole of NH3 is equal to the molar mass of NH3. So using my masses from my periodic table, I know H is 1.008, and I have 3 of them. So multiply that by 3. And then I have 1 nitrogen, so I'm going to add 14.007 to that. And that's going to give me 17.031 grams of ammonia. Now that I'm in moles, I can get rid of moles of NH3, and I can get to my moles of water. And remember, this is our mole ratio. These numbers come from the balanced chemical equation. So I have 6 moles of water, and I have 4 moles of NH3. Now, from here, if they were asking for moles of water, we would be done, but they're not. They're asking for molecules. So we need to use Avogadro's number. And we know Avogadro's number is equal to 1 mole. So since we want to get rid of moles of water, 1 mole of water is going to be on the top, and that is equal to 6.022 times 10 to the 23rd molecules of water. So now if you wanted to double check your units, grams of ammonia is gone, moles of ammonia is gone, moles of water is gone, and I'm left with molecules of water, which is exactly what it's asking for. So now we can plug in this math to our calculator. So I'm going to take 191.4 divided by 17.031, press equals, multiply it by 6, press equals, divide by 4, press equals, and then I'm going to multiply that number by 6.022 and save the exponent for the end. And for that number, I get 101.5. And then I need to remember to drop down that times 10 to the 23rd. Now, from here, we know that this is not scientific notation. So scientific notation has to be a number between 1 and 10. So what we're going to do is make this bigger number smaller by moving it 2 decimal points to the left. And now we have a number between 1 and 10, 1.015. And since we made a big number smaller, we're going to add 2 to that exponent. So it's going to be 10 to the 25th. So our final answer is 1.015 times 10 to the 25th molecules of water. All right, so number 5 is kind of a doozy, meaning we have a lot of conversion factors that we are not used to using. So I'm going to go ahead and give you those to start this problem. All right, so first up, let's go ahead and balance our chemical equation. So we have 1 carbon, so those are already balanced. We have 4 hydrogens, 1 hydrogen, so I need to multiply this by 4. Then I'm looking at my chlorines. So I have 4 chlorines here and 4 chlorines here, which is a total of 8. So dividing that by 2, that will give me a coefficient of 4. So in this equation or this problem, it says that the reaction generates 2.5 gallons of CCl4, which is my starting point. So I have 2.5 gallons of CCl4, and I'm trying to get to pounds of hydrochloric acid. So I'm going from CCl4 to hydrochloric acid. So that's going to be my mole ratio. But first, I have to get these gallons of CCl4 into moles. And my starting point is going to be my gallons to liters conversion, because I am given a density of 1.5867 grams per milliliter. So because that is going to give me my grams unit, I need to get milliliters to cancel out the milliliters unit. So first, let's get our gallons to milliliters. I have this first conversion, which gets gallons to liters. I know in 1 gallon, I have 3.785 liters. And remember, milliliters is in our density, so we need to get to milliliters. And in 1 liter, I have 1,000 milliliters. So now that I'm here and I have milliliters, I can use this density to cancel out milliliters and leave me with grams. So I know that 1.5867 grams of CCl4 is equal to 1 milliliter because it's per milliliter. So now that I'm in grams of CCl4, I can finally get to moles using the molar mass. So chlorine is 35.45 times 4, plus my carbon, which is 12.011. So that's going to give me a molar mass of 153.811 grams. And remember, whenever you get something off the periodic table, that's always equal to 1 mole. And now I am in moles, so I can do my mole ratio going from CCl4, so I want to get rid of that, moles of CCl4. And I'm trying to get to hydrochloric acid, so moles of HCl is going to be on the top. And remember, this is your mole ratio, so that comes from the balanced chemical equation. I have 4 moles of HCl, and I have 1 mole of CCl4. All right, so I'm not quite done. I'm now in HCl, but I need to get to pounds. And I can see with my given conversion factors, I have grams to pounds here. So if I can get this into grams with molar mass, that means I can use that equality to get it to pounds. So I'm just going to continue on over here because I did run out of space. So I want to cancel out moles of HCl, so moles of HCl is going to be on the bottom. And we know from the periodic table, 1 mole of HCl is going to be equal to the molar mass of HCl, which is 35.45 plus 1.008. That gives us 36.458 grams of HCl. And now that I'm in grams, I can use that equality that I was given to get out of grams. So 1 gram equals 0.0022 pounds. And now all of my units have canceled out so that I am left with pounds of HCl. So if you want to double check that, let's go ahead and switch colors here. My gallons are gone. My liters are gone. My milliliters are gone. My grams of CCl4 are gone. My moles of CCl4 are gone. My moles of HCl are gone, and I'm left with HCl in pounds, which is exactly what it asked for. So in my calculator, I'm going to do 2.5 times 3.785, press equals, times 1,000, press equals, times 1.5867, press equals, divide by 153.811, press equals. Then you're going to multiply by 4, again, press equals, multiply by 36.458, and then finally multiply that by 0.0022, and you will get your final answer, which is 31.3 pounds of HCl. All right, number 6, we are given an equation. Our aluminums are already balanced, but our bromines are not. So we have 2 on the left and 3 on the right. So that is going to be a common multiple of 6. So we'll multiply this one by 3 and this one by 2. And that changed our aluminums, and now we are balanced. So number 6 says, in the lab, you perform this reaction using an excess of aluminum and 55.7 grams of bromine. So that right there told us that aluminum is our excess reactant and bromine is our limiting reactant. So we were already given our amount of limiting reactant, so we're going to use that in our stoichiometry. The next part says you end up collecting 60 grams of product aluminum bromide. What is your percent yield? So I always tell my students percent yield is where it's at, A over T. So A stands for actual and T stands for theoretical. And then, of course, it's a percent, so you're going to multiply those values by 100. So actual is something that you get when you actually do the experiment and get your mass of product. So because when you're taking a test, you're not actually doing an experiment, this number is going to be given to you. Your theoretical is what you are solving for. So this is going to be the math or stoichiometry that you do to get your theoretical amount of product that can be made. So in this question, we have 60 grams of aluminum bromide that's actually collected. So if we are solving for percent yield, we already have the numerator of the equation, which is 60 grams. Now we just need to solve for our theoretical amount of grams, and then we're going to multiply that by 100 and get our final answer. So how do we get theoretical yield? Well, luckily we already know that it is bromine is our limiting reactant, so we only have to do one set of a stoichiometry problem. So again, just like in past problems, we're going to start with the number we are given, 55.7 grams of bromine. And we're going to solve into grams of our product. So remember, when we're converting between two substances in a balanced chemical equation, we first have to be in moles. So we have to go from grams to moles. And I know in 1 mole of bromine gas, that is equal to the molar mass of bromine gas. So bromine from your periodic table is 79.904. And we're going to multiply that by 2 because we have 2 of them. So that is 159.808 grams of bromine gas. Now I'm trying to get into my product, which is AlBr3. So I want to get rid of moles of bromine gas, and I want to end up with moles of AlBr3. Now, because my actual is in grams, I need my theoretical to also be in grams. So I have one more step after that. And remember, this here is called your mole ratio, and we get those numbers from the balanced chemical equation. So 2 moles of AlBr3 and 3 moles of Br2. So my last step is to use the molar mass to get to grams. I know in 1 mole of AlBr3, that is equal to the molar mass of AlBr3. So first step for me is going to be 79.904 times 3. Plus my molar mass of aluminum, which is 26.982. So that gives me a molar mass of 266.694. And now you can see that our units are canceling out, and we're left with grams of AlBr3. So let's go ahead and do that math. So we have 55.7 divided by 159.808. Then we're going to multiply that by 2, divide by 3, and then multiply by 266.694. That's going to give us a number, since we have 3 sig figs here, that's going to give us a number of 62.0 grams of aluminum bromide. And this is our theoretical yield. So now that we have that, we can go ahead and plug that into our equation. So 60 was our actual, 62 grams was our theoretical. So 60 divided by 62 times 100 means we're going to have a 96.8% yield. And that is our final answer. All right, so here we have a balanced chemical equation. It says to identify the limiting reactant in each of the following reactant mixtures. So we know we have 2 reactants forming a product. We also know that it's pretty much close to impossible to have the perfect amount of iron and the perfect amount of oxygen reacting to form the perfect amount of product and have nothing else left over. So essentially what I mean by that is one of our reactants is going to run out first, which means we can no longer make any more product. And whichever one runs out first is going to be our limiting reactant. So how do we solve for that? we're going to take our values of our reactants and we're going to convert them into the same product. Now in this equation, it's nice and simple because there is only one product. If there are multiple products and it doesn't tell you, you can just pick one. If it tells you, solve into that specific product. So first, starting with A, we have 0.288 moles of iron, and we have 0.240 moles of oxygen gas, and it wants to have us solve for the limiting reactant. So again, limiting reactant, we are solving into the same product. In this case, there's only one. So we want to get rid of moles of Fe, and we want to end up with moles of Fe2O3. Same down here, we want to get rid of moles of oxygen gas. We want to end up with moles of Fe2O3. So these are our mole ratios from the balanced chemical equation. 2 moles of Fe2O3, we have 4 moles of iron, and we have 3 moles of oxygen gas. So for our top equation with iron, we have 0.288 times 0.5. That's going to give us 0.144 moles of product that is being made. And then for our second part with oxygen gas, we have 0.240 times 2 divided by 3. So that's going to give us 0.160 moles of Fe2O3. So now looking at these two theoretical yields, I have 0.144 and I have 0.160. So as we can see, this number is clearly smaller, which means after iron produces that 0.144 moles of our product, there is now no more iron left, which means this number is impossible to make. So that means our smaller amount is our theoretical yield, and whatever produces the smaller amount is going to be our limiting reactant. So for A, our limiting reactant is going to be iron. Now let's do the same process for B. So in this case, we are in grams. We need to get out of grams and get into moles. I know in 1 mole of iron, that's equal to the molar mass of iron, which is 55.845 grams. And same goes with my O2. I know 1 mole of O2 is equal to the molar mass of O2, which is 31.998 grams. Now that I'm in moles of our reactants, I can convert into moles of my product. I want to get rid of Fe, and I want to get rid of O2, and I want to end up with moles of Fe2O3. Remember, these are called your mole ratios, so this is where you get them from the balanced chemical equation. So I have 2 moles of Fe2O3, I have 4 moles of iron, and I have 3 moles of O2. So we can see here that iron produced our theoretical yield, or our smaller number. So iron, again, is our limiting reactant for B. Now we're going to do the same thing for C. All right, so this one's a little different. We're given atoms and molecules, which is Avogadro's number. So in order to get into moles, we're using 1 mole is equal to Avogadro's number. And we want to cancel out those atoms or molecules. So we know 1 mole of iron is equal to 6.022 times 10 to the 23rd atoms of iron. And we also know that 1 mole of O2 is equal to 6.022 times 10 to the 23rd molecules of O2. And now that I'm in moles, I can go ahead and convert that into my product. So moles of Fe is what I want to get rid of. Moles of Fe2O3 is what I want to end up with. Same down here, I want to get rid of moles of O2, and I want to end up with moles of Fe2O3. And we get those from our balanced chemical equation. So 2, iron has 4, and oxygen gas has 3. All right, so if you want to plug all of this with the exponents into your calculator, that's totally fine, but I do this a little bit differently. So in my calculator, I do 1.45 divided by 6.022, and then I multiply that by 0.5, which is 2/4, and that gives me 0.120 for 3 sig figs. Now I have to deal with my exponents. So I have 10 to the 24th in the numerator, and I have 10 to the 23rd in the denominator. So when I cancel those out, I'm left with 10 to the 1st in the numerator. So I'm just going to multiply this number by 10 to the 1st, which would also be multiplying it by 10. So my final answer is 1.20 moles of Fe2O3. Now let's do the same thing for our bottom equation. So I have 7.21 divided by 6.022 multiplied by 2 and then divided by 3. That gives me 0.798. And then looking at my exponents, those are completely gone. So I'm just left with 0.798 moles of Fe2O3. And since this number is smaller, that means O2 is my limiting reactant for C. All right, number 8 says that sucrose reacts with potassium chlorate according to the following balanced equation. Suppose 3.5 moles of sucrose are mixed with 21 moles of KClO3. Identify the limiting reactant, then calculate how many moles of each product will be formed in this reaction. So first step is we have to figure out which one of these reactants is going to limit how much product is being made. So we're going to start with the numbers we are given, which is 3.5 moles of C12H22O11 and 21 moles of KClO3. So using these two values, we're going to figure out what is limiting. So let's first start out with CO2. So if I'm trying to get both of these into the same product, I'm first starting with carbon dioxide. I want to end up with carbon dioxide, so that's going to be on the top. And remember, I can go right into the mole ratio because I'm in moles. If I wasn't starting with moles, I'd have to convert to moles first, but I'm already there. Now on the bottom, I want to get rid of moles of sucrose. And I want to get rid of moles of KClO3. And remember, these numbers come from the balanced chemical equation. So CO2 has 12 moles, sucrose has 1, and KClO3 has 8. So sucrose is going to produce 42 moles of carbon dioxide, and KClO3 is going to make 31.5 moles of carbon dioxide, which with the correct sig figs is going to be 2 moles. I'm sorry, 2 sig figs, so 32 moles. So because our theoretical yield for carbon dioxide was 32 moles, that was produced by KClO3, and that means KClO3 is our limiting reactant. So now that we know our limiting reactant, we can go ahead and just use that number to convert to moles of each product, which is what it asked for. So I'm going to take that 21 moles of KClO3, and now I'm going to find out how much water and how much KCl that would make in moles. So first, let's start with water. In order to get 2 moles of water, I need to use the mole ratio. I'm canceling out KClO3, so that's going to go on the bottom, and water is going to go on the top. And remember, mole ratio is when you get the numbers from the balanced chemical equation. So I have 11 moles of water, and I have 8 moles of KClO3. So now in my calculator, I'll do 21 times 11, and then divide that number by 8. And in my calculator, I get 28.875, but because my given number is in 3.5 and 21.0, my lowest number of sig figs is 2, so I need to have that number in 2 sig figs. And for my last one, I'm converting to KCl. So again, I need to get rid of moles of KClO3, so they're going to be on the bottom. And I want to end up with moles of KCl, so it's going to be on the top. So the 8's cancel out, so I'm just left with 21 moles of KCl. And that is number 8. All right, so number 9, you were given a balanced chemical equation, and you were also given grams of both of your reactants, so BF3 and H2. Part A says to identify the limiting reactant, and then part B says to calculate the mass of HF generated. So remember, whenever we're finding the limiting reactant, we're converting our reactants into the same product. Now, because part B says it's solving for HF, make sure for A you are solving into HF so that you do not have to redo your math to solve for part B. So again, just like in the previous problems, we're going to start with what we're given. We're given 40 grams of BF3, and we're given 5 grams of H2. So in order to find what is limiting, we are solving into the same product, in this case, HF. So in order to go from our reactants to hydrofluoric acid, we have to first be in moles. So step 1 is to convert from grams into moles using 1 mole is equal to the molar mass of that substance. So 1 mole is equal to the molar mass. For BF3, I have fluorine, which is 18.998 times 3, plus boron, which is 10.81. So that's going to give us 67.804 grams of BF3. And then for H2, it's going to be 1.008 times 2, which is 2.016. And now that I'm in moles, I can go ahead and do the mole ratio to go from my reactant into my product, which is HF. And remember, this is our mole ratio where we get the numbers from the balanced chemical equation. So I have 6 moles of HF, I have 2 moles of BF3, and I have 3 moles of H2. Now, since B is asking for mass of HF, I'm just going to take this one step further and solve for mass now so I don't have to go back. And I know in 1 mole of HF, that is going to be equal to the molar mass of HF. So fluorine is 18.998 plus hydrogen 1.008. So that gives me 20.006 grams of HF. So now let's go ahead and solve. On the top we have 40 divided by 67.804. Then we're going to multiply by 3 because that's 6 over 2. Then we're going to multiply that by 20.006. So that gives us 35.4 grams of HF. Then we're going to do the same thing to our other stoichiometry equation. So 5 grams divided by 2.016, press equals. Multiply that by 2 because that's 6 over 3. And then multiply that number by 20.006. That's going to give us 99.2 grams of HF. So what does this exactly mean? So when we're looking at this reaction, we can see that we're starting with 40 grams of BF3 and 5 grams of H2. When we mix those two together, we're going to start by being able to make 35.4 grams of hydrofluoric acid. Now, once we make this amount, all of our BF3 is going to be gone. So we can no longer make any more product. So this number here really doesn't have any value. So this 35.4 grams of hydrofluoric acid is called our theoretical yield, or the maximum amount of product that can actually be made. And because BF3 is the one producing our theoretical yield, BF3 is going to be our limiting reactant, and H2 is what we're going to have left over at the end, which is known as our excess reactant. So the answer to part A is BF3. The answer to part B is 35.4 grams of HF. Now, part C of that same question says calculate the mass of excess reactant that remains when the reaction is complete. So we know from part B that 35.4 grams of hydrofluoric acid can actually be made, correct? We also know that H2 is going to be left over. So by using our 35.4 grams of HF, we can convert into amount of our excess reactant, and that's going to tell us how much was used up to make that 35.4 grams of hydrofluoric acid. So let's start there. So we're essentially going backwards back into H2, which is our excess reactant. So first step is to get rid of grams, and 1 mole of HF that is equal to the molar mass of HF, which is 20.006. Now that we're in moles, we can do the mole ratio. So we're getting rid of HF and we are ending up with our excess reactant, which is H2. And then because we were given 5 grams, we want to be in grams. So in 1 mole of H2, that's the molar mass of H2. And then remember mole ratio, those come from the balanced chemical equation. So 3 and 6. So now we can go ahead and solve 35.4 divided by 20.006. We're going to multiply by 0.5 and then multiply by 2.016. So that gives us 1.78 grams of H2. So think about what this means. This is how much product we can actually make. So by taking that number and converting it back into our excess reactant, that tells us that 1.78 grams of hydrogen gas was used up in the reaction. So if 1.78 grams was used up and we started with 5 grams, we know that if we just subtract that number, that is going to give us how much is left over. So our answer to part C is 3.22 grams of H2 in excess. All right, and then the final part for number 9 is part D. When this reaction is performed in the laboratory, the percent yield of HF is 72.6%. What was the experimental yield of HF? So remember we talked about earlier in the video, percent yield is where it's at. A over T times 100. This question is kind of worded a little tricky. It's saying we already know our percent yield. Our percent yield is 72.6%. We also know our theoretical yield because we calculated it. So we also know what's on the bottom, which is 35.4 grams of HF. And then we know we're going to multiply this by 100. So our only missing value here is the actual amount. So we know simple algebra, right? So if we want to get rid of this 100, we need to divide both sides by 100. So that means I'm going to have 0.726 equals x over 35.4. So now to get x by itself, we're going to multiply 35.4 on both sides. So I have 35.4 times 0.726. So that means x, or my actual yield, is going to be 25.7 grams. And that is of HF. And that is our answer for part D. All right, and then the very last question of this review. Pure carbon reacts with sulfur dioxide gas, producing liquid carbon disulfide and carbon monoxide gas. Write the balanced equation for this reaction. So first we have pure carbon. Carbon is just C. It's not diatomic. And that is going to be a solid. it's going to react with sulfur dioxide. So react with means an and sign. Sulfur is S, and di means two. Oxide is oxygen, so two oxygens. And it says that it is a gas, so we're going to put a G next to it. Then it produces, meaning we're on the product side, liquid carbon disulfide. So that's carbon. Di is two, so two sulfurs. And that is a liquid, so we're going to put an L next to it. And then it also makes carbon monoxide gas. So carbon is C, mono means one, so one oxygen. And then we know it is a gas. So now last step for part A is to balance it. So I have one carbon on each side. I have one sulfur on the left, two sulfurs on the right. So I'm going to multiply this one by 2. That means I now have 4 oxygens on the left and only 1 on the right. So I'm going to put a 4 here, which is then going to give me 5 total carbons on the right side. So now I'm just going to put a 5 in front of carbon on the left side. And that is the answer to part A. Part B says what mass of carbon monoxide will be produced if 40 grams of carbon are allowed to react with 95 grams of sulfur dioxide. So this is again theoretical yield question. So we're trying to figure out what mass of our product, carbon monoxide, can be made with those two amounts of reactants. So starting with what we are given, which is our 40 grams of carbon and our 95 grams of sulfur dioxide, SO2. So if we want to get into carbon monoxide, the first thing we need to do is convert to moles. So in 1 mole of carbon, that's equal to the molar mass of carbon. And 1 mole of SO2, that is equal to the molar mass of SO2. Oxygen is 15.999 times 2 plus sulfur, which is 32.06. That's going to give us 64.058. Now that I am in moles, I can go ahead and convert into carbon monoxide. So since I want to end up with carbon monoxide, it's going to be on the top. And I want to get rid of my reactant. So I want to get rid of moles of carbon, and I want to get rid of moles of SO2. And remember this mole ratio, we get the numbers from the balanced chemical equation. So we have 4 moles of CO, we have 5 moles of C, and we have 2 moles of SO2. And then finally it asks for mass, so we do need to have one more step. And we know in 1 mole of CO, that's equal to the molar mass of CO. So to get carbon monoxide, I do 12.011 plus 15.999. That gives me 28.01. So for my top stoichiometry, I have 40 divided by 12.011. I'm going to multiply that by 4, and then divide by 5, and then multiply by 28.01. So that gives me 74.6 grams of CO. I'm going to do the same thing with the other one. I have 95 divided by 64.058. Then I'm going to multiply that by 2, and then multiply that by 28.01. And that is going to give me 83.2 grams of CO. So as you can see, our limiting reactant, or the maximum amount of product that we can make, is 74.6 grams of carbon dioxide. So this is our theoretical yield. And that is produced by our limiting reactant, which is carbon. So it says what mass of carbon monoxide will be produced. Carbon monoxide will be produced. And the answer to that is 74.6 grams of carbon monoxide. Then it says what mass of excess reactant is left over. So remember, to get our mass of excess reactant left over, we have to take our theoretical yield, which is the actual amount of product that can be made. So that is 74.6 grams of CO. And we have to convert that into our excess reactant, which is SO2. And that's going to tell us how much was used up. So first, let's get carbon monoxide into moles. 1 mole of carbon monoxide is equal to the molar mass of carbon monoxide. Now that I'm in that, I can go from moles of carbon monoxide to moles of my excess reactant, which is SO2. These numbers come from the balanced chemical equation. And then finally, I want to get that in grams. So 1 mole of SO2 is equal to 64.058 grams of SO2. And now I can solve for amount of SO2 used. So 74.6 divided by 28.01. Then I'm going to multiply that by 0.5 and then multiply that by 64.058. And that gives me 85.3 grams of SO2 used to make our product. So remember, from the original equation, we started out with 95 grams of SO2. We used up 85.3 grams of SO2, which means in our calculator, if we take 95 minus 85.3, we have 9.7 grams of SO2 remaining. All right, and that is your Chapter 10 review. If you have any questions, please feel free to reach out. I'm happy to help. Have a great day.